Welcome everyone. In this video, we will be discussing about transmission lines. Transmission lines are commonly used in power distribution or in communications. Power distributions takes place at low frequency, usually in 50 to 60 hertz, and communications takes place in high frequency, like in RF frequency or microwave frequency. A transmission line is basically used to connect a source to a load. Let us think about this is a source or generator, and here we have a load, and this is the source or generator. The transmission line is used to connect the source with load. Here, so this is the current path, and here this is the returning current path. So this current is I, and this is the return current. The transmission line basically used to connect a source with the load. Here the source could be a hydroelectric generator, a transmitter, or an oscillator. In the microwave lab, you use a GAN oscillator to produce microwave frequency. And for load, we can use a factory or an antenna or an oscilloscope. So there are many types of transmission lines. The mainly used transmission line are two-wire transmission line. So if you look at construction of a two-wire transmission line, you will see one wire here and another wire here. Wires are wrapped by an insulator. So this is the insulator. If you look at the cross-sectional area, you can see the two conductors here are surrounded by dielectric substance or an insulator. Mainly, we discuss about the electric parameters like the conductor and the magnetic parameters like the permeability of conductor and conductivity, permittivity of the dielectric material. So another type of transmission line is coaxial cable transmission line. In this type of transmission line, we have a conductor here, circular conductor here, and that is surrounded by another conductor. And in between this, we have an insulator that's separating the inner conductor from the outer conductor. Also, the outer conductor is surrounded by another dielectric or insulator. So if you see the structure here, we can see the copper wire is the inner conductor and dielectric material and another copper mesh, another conductor here is also surrounded by another insulator. So Rogers cable is this type of conductors, coaxial cable. So you can see a two-wire type transmission line with three phase. So here you see one phase, another phase and third phase for three-phase communications. There are a lot of protective gears and apparatus connected here like A, B, C. Parallel plate transmission line. So you see we have two plates here. The plates are separated by a dielectric material. You can also see their cross-sectional diagram like this. And in addition to this, we might have a strip line. So there is a conductor is sandwiched between the ground plane. And also we do have conductors, and this is substrate is surrounding by this the conductor. And this is microstrip line. You can see the printed circuit board design with microstrip line, this type of transmission line, PCB. This is coplanar type waveguides, and this is the rectangular type waveguides. You may see this type of waveguide in the microwave lab. So we have a transmission rectangular types of structure here. In this cavity, the electric signal is propagating through this cavity here, and this is surrounded by metal structure. And this is also optical fiber, another type of high frequency transmission line. So basically, rectangular waveguide and optical fiber are used for high frequency transmission line. So these are the commonly used transmission lines. Now we want to discuss about the transmission line equations. Basically, we want to see the voltage and current equation, also the wave equation. for two-wire transmission line. So let's say we have one wire here. The wire one first conductor is this one, and the return path is here. So this is the source is connected this side. This is the source, and this load will be connected here. Let's assume the current I is coming from the source, and I plus delta L is the current towards the load. So the current here will be flowing through the conductor, and also there will be a current flowing through the dielectric. So this type of current is called the leakage current, because you know you will be a charge, positive charge accumulated on this plane, and negative charge will be accumulated here. So because of this charge distribution, you will find a displacement current here, and the voltage at this side, input side is V and the output side is V plus delta V. Now we are interested in the circuit resistance like this R. As you know, the resistance depends on the length of this, so you can write length, and the conductivity of this like sigma, and the cross-sectional area like M. So we might have a resistance, electrical resistance for this conductor. So we might have a resistance, and also we might have inductance that is equal to mu of this conductor, and A, the cross-sectional area of the conductor over the length of the conductor. So this is the inductance. So basically we are interested about the parameter like mu and sigma. Sigma contribute to the resistance and mu contribute to the inductance of this, because when current will be flowing, it will produce a magnetic field here, and this magnetic field basically can be determined by using this mu. And when the charge accumulate on this plane and negative charge accumulate here, that will produce a magnetic field, and you will see the there should be some resistance for this dielectric material. So you might say some resistance here, that is we are discussing about conductance, and also we can see the capacitance of this system. So C equal to epsilon A over the D. So here we discuss about epsilon A over D. Epsilon is the permittivity of the dielectric material, and also you can find G. G will be just opposite to this sigma A over L. But this sigma is not same as this sigma. This sigma is for the dielectric material, and this is for the conductor. So you can write for the sigma C, and this is sigma D for dielectric material. This A is not same as this A. This A is the area of this dielectric substance. This D is the distance between these two cables. So you can see C and G for the dielectric material, and R and L for the resistive conductor. So here we have R and L. R and L. So R is basically we measure for per unit length, and L for per unit length. So the total R will be R. Let's say we are taking a segment of this wire that has the length delta Z. So R will be R times delta Z, and L will be L times delta Z. That is the total R and L. R and L distributed throughout this conductor, but we are taking a lumped value here. Similarly, the conductance and the capacitance also distributed throughout this dielectric material, but for convenience we are assuming they are basically at this point. G and total is Z times delta Z, and C times delta Z is here. So this is my current delta I, and here the coming current is I. Coming current is I from here, and this. And the voltage here is V, and here is V plus delta V. Now we are going to write Kirchhoff's voltage law and current law. We are not trying to find the wave equation in terms of electric field or magnetic field. We want to find them in terms of voltage and current, because transmission line or this concept can be applied to power system or transmission or distribution system or some other power process. That's why we want to find the transmission line equation with respect to voltage or current, not electric field or magnetic field, as we did for lossy dielectric. It's a good conductor. Now we will be applying Kirchhoff's voltage law here. So if we apply Kirchhoff's voltage law in this loop, so let us apply Kirchhoff's voltage law in this loop. So you will see the voltage here, the voltage over here is equal to the voltage dropped in this line plus the voltage here. So if we use the Kirchhoff's law, so it will be voltage plus the voltage drops here. So how many voltage drops will be here on this along this path? So that is R plus Z delta Z plus L plus delta Z. So you can write R delta Z times I. That's the voltage drop here, RL. So this is the total resistance times I voltage, and here the voltage will be J. So impedance is J omega J omega L delta Z. So this is the inductive reactance times I. And the voltage here, so we are starting a negative sign, that this will be a positive. So V plus delta V equal to 0. Or simply we can write V equal to this part. So V plus delta V. So you can cancel out this one. So I will come up with delta V over delta Z with negative R plus negative J omega L times I. So you can write it negative, positive, I. Similarly, you can apply Kirchhoff's current law at this point. So here you see the current entering is I, and current that leaving here or entering from here is delta I. So current that entering here, going this way, is the delta I. So I plus delta I is equal to I plus delta I. So you see here the current here. Now we can write down this KCL with respect to the voltage. So we can write it like I. This current entering here is I, and current in this branch will be Z. So this is the voltage V plus delta V times the conductance will be the current here, and V plus delta V times this capacitance will be the current here, and this is the current. So that write KCL here, delta I is the current. Basically we are writing V plus delta V, Z plus j omega C delta Z. So just we are writing the current delta I. So delta I is, so we are writing not A, we are applying KCL at this point. So KCL at this point, if you write KCL at this point, you see the current here and current here will be the delta I. So delta I, let us apply KCL at this point. So assuming the current in this branch is outgoing, here also outgoing, and the voltage at this point is V plus delta V, and here it have grounded. So now we can write the node current equation here. So if you write node current equation, you see the current leaving here is delta I plus the current leaving here is will be V plus delta V times Z delta Z. So you see voltage times conductance gives you the current. Also you can write here will be J omega C delta Z times V plus delta V equal to 0. As we can make an approximation here, you see the voltage regulation of a transmission line will be very low. So you can write it like V plus delta V is approximate to V. So the voltage variation from the source to generator will be very low. So you can write V plus delta V is V. So if we approximate this, we can write delta I over delta Z equal to minus Z plus J omega C times. So we got delta I plus delta Z times the. Now we got this expression using uh, Kirchhoff's voltage law. Like if we assume that my transmission line length, the length of the segment is very low, small, then we can like delta V over delta Z can be written as dV over dZ. So I write dV over dZ is equal to this. Similarly, we can write di over dZ is this. So you can get the voltage derivative with respect to the Z and current with respect to the Z is this. Now, if I take uh, again derivative to this, so that will be d square v over dz square r j omega l or j omega l and di over dz. So now di over dz we already obtained here. So I substitute this value in this line. So you will get d square v dz square equal to this. So now you see this expression is a second order differential expression with 0 at the right hand side. So this is a homogeneous second order differential equation and very similar to the wave equation that we have developed before. So if we assume that R plus j omega L times G plus j omega C equal to gamma square, then this is very similar to the wave equation that we obtained for dielectric medium and good conductor. So here we can assume that gamma is R plus j omega L and G equal to j omega C. And we define gamma as the same that we did for before. So this is called the propagation constant. And this is has two parts, that is alpha and another part is the beta. Alpha is the attenuation constant, beta is the phase constant. So we can write these transmission line equations like this, or if you want to write with respect to the current, you will come up with this equation. Now the solution to this equation will have one positive term that is propagating in positive z-axis and another is the propagating in negative z-axis. So the solution we can write it like v0 at e to the power gamma z, v0 minus e to the power gamma z. So it is negative gamma z that is propagating in positive z direction. So this is in positive z direction, and this is in negative z direction. So we got the uh, complete solution on the one voltage is propagating positive and another voltage in negative z direction. And similarly, the current, if we solve it, the current will get the solution like this. So this is what we keep this is as a negative as we did for the electric and magnetic field solution. Like recall the total wave equation. So we got if electric field polarized in the same direction, then magnetic field will be opposite. So we use the same sign convention here plus and this is for minus. So now I0 plus basically will be V0 over Z0. and I0 minus will be negative V0 over Z0. And the Z0 is J omega L over gamma, or R omega L J plus omega C. So basically what we got before. So let's say we got V0 plus the voltage. Let's assume we take only V0 plus e to the power negative gamma z. Now if I take dV over dz, you will get V0 plus and negative gamma e to the power negative gamma z. And dV over dz, if you recall the previous problem, you see dV over dz is R negative Rj omega L times I. So you can substitute this. So it will be negative R j omega L times I. So now you see you can write it like I equal to V0 plus gamma e to the power. So that's the voltage. V0 plus e to the power gamma that is the voltage. So you can write voltage minus negative gamma. So they cancel out this negative sign from both sides. So you'll get I equal to voltage gamma over this. So and you see our voltage equal to, so you can write voltage over current equal to R plus j omega L over gamma. So R plus j omega L over gamma and voltage over current can be written like impedance. Transmission line impedance Z naught V over I can be written like R plus j omega L over gamma. And if you substitute gamma that we have obtained before, gamma equal to square root of R plus j omega L times J plus sigma C, you will come up with this expression. So now Z0 is called the characteristic impedance of the transmission line. We found intrinsic impedance like this formula for some other material like for free space or intrinsic dielectric material. Now we are using this is the shunt admittance or conductance and capacitive susceptance for the dielectric material. So that's defined as Z naught. And the characteristic impedance Z naught is of a line is defined as the ratio of forward voltage to the forward current wave I0 plus at any point. So it also can be written like Z naught equal to V0 plus over I0 plus, or can be written like Z naught equal to negative V0 minus over I0 minus. Okay, and this characteristic impedance Z naught also called the source impedance. Now, from the obtained frequency domain, voltage and current expression, we can get the time domain expressions for the respective terms, like the voltage in time domain can be written as V0 plus e to the power minus alpha z cosine omega t minus Bz. This is alpha is the attenuation constant and B is the phase constant, and alpha plus beta is the propagation constant. Similarly, the current wave in time domain can be written like this. So if you want to find the V minus, the voltage or current in the opposite direction, then you have to change the sign here. So it will be plus alpha, and here it should be positive beta z. Assuming that the conductivity of the conductor in a transmission line is, as usual, very high. The wave on the line is approximately TEM. We also can find the energy velocity or the phase velocity U by using this formula omega over beta. I would like to mention that a transmission line are usually characterized in terms of the transmission line characteristic impedance Z0 and the velocity of the propagation. So based on the characteristic impedance and velocity, propagation velocity, we categorize the transmission line in three different ways. One is the lossless transmission line, another distortionless transmission line, and low loss transmission line. So let us consider the propagation constant expression here, alpha plus beta and gamma. So a lossless transmission line is a transmission line is said to be lossless if the conductor of the line are perfect, that is conductivity is infinity, and the dielectric medium between the lines is lossless, that its conductivity is zero. So if this condition meets, if conductivity is infinity, that means resistance of the conductor will be zero, and if the conductivity of dielectric is zero, that means the conductivity J is zero. So as you see the for resistance, so as you see for the conductor, we know that conductor R, the resistance of the conductor is equal to L sigma C times A. So as the conductor has very high conductivity, so this will be infinity, and 1 over infinity gives you 0. So resistance becomes 0. And for dielectric, you have, G is equal to sigma dielectric times A over like L. So here sigma D is very small, 0. So the conductivity of the dielectric material will be 0. So we are getting R equal to 0 and G equal to 0 for lossless medium. Lossless means there will be no resistance of the conductor and conductance for the dielectric material. So we are getting this, and if you put R and G in this equation equal to 0, R equal to 0, G equal to 0, you will get J omega L, J omega C, and that's basically equal to J omega square root of LC. So this is very similar to the phase constant beta. Phase constant beta we have learned about J omega mu and epsilon, right? So we learned it before. So here mu is something similar to the L inductance, and epsilon is similar to the capacitance. So at this case, you see attenuation constants become zero because this is purely imaginary. So there is no real part. Attenuation constant is zero, and phase constant is this. So that means you are getting the phase velocity or speed of propagation by using this formula, omega over beta, and beta equal to this. So you will get 1 over square root of mu c, and the characteristic impedance. Now if you want to find z naught, the formula is this divided by this. So if you put R and J 0, so it will be L over C, the square root of L over C. So that means we are getting a transmission line, lossless transmission line is basically like this. So here what is going to happen, the current charges up this capacitor and produce electrostatic electric field here, and then it discharges through this inductor and produce a magnetic field, and then it charges up the next capacitor here and discharges through the next inductor. So and this is the way how the electromagnetic signal propagates here. So at first the current charged the capacitor and established an electric field, then it discharged through the inductor and produce a magnetic field. So you see there are a phase difference between this capacitor and inductor because they both of them are not working at the same time. So when capacitor is working, inductor is discharging, capacitor is charging, inductor is discharging, or like this. So now if you think about distortionless transmission line, distortionless transmission line means is the line on which the attenuation constant alpha and the phase velocity are frequency independent. So no matter the operating frequency of the signals, alpha and the speed will not depend on the frequency. That's called the distortionless system. Transmission line is faithful, so it can carry any frequency signal without distortion. So you see here we say R plus j omega L. The condition is R over L will be G over C. So this, now if I take R and G as a common factor, so it will be 1 plus J omega L over R. And now alpha, so here you see the real part is this one, and the imaginary part will be j omega L R times this one. So you can write j omega g over r. So here j omega l, sorry, omega l and g over r is equal to c over l. So you can write c over l. So if you cancel this one l here, it will square root over lc. So we get the beta equal to omega lc and alpha equal to this. So you see now alpha is independent to the frequency. So no matter what is the frequency of the signal, the attenuation constant is fixed. It's constant. It is not independent to the frequency. So the signal will be distortionless. There will be no distortion to the signal. But phase constant is a so you also see the speed of this is also independent to the frequency. Transmission line, the speed of propagation is independent to the frequency. Now the characteristic impedance, we can write R plus j omega L over this. So if you take L and C as a common factor, you will see like this. So here R over L is equal to G over C. If you put G over C here, then these two terms will be similar, same. So you can get Z naught equal to L over C. You see the characteristic impedance also independent to the frequency. So it is like the ratio of square root of inductance and the square root of capacitance. Now for low loss transmission line, we are assuming R is very, very small than omega L and G is very, very small than omega C. So now if we take the gamma expression here, so this gamma is like this. So now we can write it like alpha and beta. We can separate it like this, j omega L. So we can take this, break down this one, so it's a square root of this. So you can use a binomial theorem and expand this, we'll get the expression like this. And also here we can write this. So now if you multiply these two terms, so that will be 1 plus r plus z. There will be r times z, and this omega is very high, so you can easily uh, skip that part. So you will come up with this one. So here you see this term has a j, and this j will cancel out. So this will be the real term. This r over this, g over this will be the real part, and this term will be times 1 is the imaginary part. So imaginary part is this. So you can get the phase constant, the same expression for distortionless and lossless transmission line. And this is the attenuation constant is equal to r over 2. So you cancel out this omega and it will be c, the square root of c over l. And this term will be c over 2, the square root of l over c. So now if you take L over C as a common factor, Z naught, so this is my attenuation constant here. And if you want to find the Z naught, the impedance, so you can write down the expression like this way. And then you can approximate this. This value will be very high. So Z naught will be again similar L over C. So this is the characteristic impedance. So no matter for low loss, lossless. So for lossless, we got alpha equal to 0. For this is for lossless, and we got alpha equal to square root of alpha equal to square root of r times g for distortionless, and alpha equal to this one for low loss transmission line. But for beta is same for uh, all the transmission lines, and also the characteristic impedance is same for all the transmission lines. Only the attenuation constant differs. So it is 0 for lossless. This is square root of rz for distortionless, and this is this expression is for low loss transmission line. So let us find the voltage and current field in the transmission line. So we have one voltage field that is propagating in the positive z-axis. So let's assume this is my z equal to 0 at this interface. So you connect the load here. So this is my load side at z equal to 0. then this side is load Z increasing, and at the generator is connected here, so that side will be Z equal to negative L. So if I take the length of this transmission line is L, so any measure distance from measured from the load is negative, because this is load is at 0. So now you see at this point we have a wave that is propagating in this direction and towards the load, so that is V plus, and a wave is reflected toward the generator, that is V minus. So this is the reflected wave, and this is the transmitting wave, or transmitted wave. And here we have a total wave. So total wave is the sum of this plus this, that the total wave. Similarly, the current, this is the forward current I plus, and this is the returning current I minus, or the reflected current I minus, and I is the sum of this and plus this. So I is the total current I at any point is it. So at any point we have voltage V and I, at the load reflected voltage is V minus and I minus, incident voltage or the forward voltage is V plus I plus. So now we are going to use these expressions for finding the reflection coefficient. So consider a transmission line with propagation constant gamma and the characteristic impedance Z0 and the load impedance ZL, at source voltage as Vg, and the source impedance is ZZ. So voltage at any location. So at voltage at any location will be the voltage in forward voltage propagating positive Z axis, and the reflected voltage minus B. So now this is the forward voltage, this is the reflected voltage. So sum of this is the total voltage at any point. Similarly, current is I1 plus minus it is, and I can be written voltage over Z naught e to the power gamma, voltage minus over Z naught e to the power gamma. So we got the voltage at current general expressions. Now if we rewrite this expression voltage and current, so we can take V0 plus as a common factor, then we will get gamma L, and this will be V0 minus over V0 plus, that is replaced by the reflection coefficient at the load. And similarly the current can be written like V0 plus Z0 to the power gamma Z, and the ratio of this will be gamma L to the power gamma Z. So now the gamma L, this is called the reflection coefficient at the load, is equal to V minus reflected wave over the incident wave or forward voltage at Z equal to 0. Or simply you can write V0 minus V0 plus. So V minus basically meaning that reflected wave, and V plus is the forward voltage wave, but V0 minus is the magnitude and V0 plus is the magnitude. So now at reflection coefficient at any point, so let's say gamma Z, and so we take V minus and V plus, so the reflected voltage and the incident voltage of at any point Z, and here the expression is V naught e to the gamma Z. This term is basically we define it like gamma L, gamma L, and this is the coefficient of this. So as you see here, reflection at any point is equal to reflection at load times e to the power 2 gamma Z. So meaning that reflection is not constant, but reflection at the load will be varied exponentially with a sine or cosine function. So you might see the reflection at the load, reflection at any point will have the magnitude, same magnitude, but with the phase angle. So the phase angle here. So this is contributing to a phase angle. So reflection at any point, but the same magnitude at reflection at load. So if I go to the previous slide here, so we can find the reflection at this point, 0 minus over V0 plus. But if you want to find reflection at any point, at a point here, that is equal to the value that we got here and with a phase angle. And the phase angle basically comes from how much you are traveling from here to here. So that's contribute to this phase angle. Now, if you want to find the voltage expression, so if you see the voltage expression can be written as B0 gamma Z. So if you take the entire thing as a common factor, entire thing as a common factor, you will get 1 plus gamma because this will be V0 naught over V0 I e to the power 2 gamma Z and that is equal to gamma N e to the power 2 gamma Z. So you can write gamma. Similarly, the total current can be written as like this. For the reflection coefficient, so what we got for in previous chapter, we got reflection is equal to eta 2 minus eta 1 over eta 2 plus eta 1. So we might get a similar formula here. To get a similar formula, let us find the reflection at this point. So at this point, we got the reflection value gamma L, and we can find the voltage and current here, voltage and current at this point. So here voltage at this point will be voltage at Z equal to 0, and you know the voltage, the total voltage expression is like V0 plus e to the power negative gamma Z plus V0 minus e to the power gamma Z. So now if you put Z equal to 0, it will be V0 plus V0 minus. So if you take V0 plus as a common factor, you will get 1 plus gamma L. Similarly, the current will be V0 plus over Z0 1 minus gamma L. But this voltage is VL at load voltage and at load the current will be IL. Now VL over IL can be written like the load impedance. So the load impedance is ZL is equal to VL over IL, and if you take this one you will get divide this part. So B0 plus if you cancel out, you will get Z naught 1 plus gamma L over 1 minus gamma L. Now if you solve for gamma L, you will get ZL minus Z naught divided by ZL plus Z naught. So you see here the very similar formula. So this is the impedance of the second medium, the impedance of the first medium. But here we don't have two mediums, but we do have a load impedance and the line impedance, characteristic impedance of this line. So the line has impedance Z naught, so Z naught, so you can write ZL minus Z naught divided by ZL plus Z naught. So line Z naught is the impedance of this transmission switch line and ZL is the impedance of the load. So ZL minus Z naught over ZL plus Z naught. So that's the reflection coefficient. Similarly, you can find the transmission coefficient. So if the signal is transmitted here, so the transmission coefficient is equal to Vt over Vi at load Z equal to 0, or you can write it like this, or you can simply write it like transmission coefficient is 1 plus gamma L. Now, if you want to find the input voltage and input impedance, so to find the input impedance, we are taking Z the is equal to, let's say we have a voltage here at this point, the voltage is V, and at this point the current is I. So the impedance at this point will be V over I, and V over I can be written like V equal to this V0 plus e to the power gamma Z and gamma L e to the power gamma Z, and I is P0 over Z naught e to the power gamma Z and this. So if you can write it like e to the power gamma Z, if you put gamma L here, gamma L as we got before is equal to ZL minus Z naught over ZL plus Z naught. So if you substitute this here, substitute this gamma L here, you will come up with this expression. So the impedance is Z naught ZL minus this. Now, if you have a lossless transmission line, then gamma will have no alpha term, so it will be only J beta. So if substitute then is JZ is equal to Z and beta Z. So you'll get the formula like ZL minus Z naught tan beta L, Z naught tan beta Z. But beta Z is the value measured here, and that is put on the negative side to this. So you can write it Z equal to negative L. So if you put Z equal to negative L, we'll get Z naught equal to ZL, Z naught tan beta L, Z naught plus Z tan beta L. And this is the impedance at any point. It is called the input impedance. The input impedance is the impedance at any point. So impedance, if you want to measure the impedance at any point, you can measure like this. So if you look at this thing here, so input impedance or the impedance at this point is basically including the load impedance plus the impedance of from here to here. That's the characteristic impedance and also the length, contribution from the length. So we have three factors to consider for finding the impedance here. One is the load impedance that is connected here, the characteristic impedance of the transmission line, and the distance. So you see the input impedance is a function of ZL, Z0, and the distance L, as well as the beta phase constant and L. Phase constant and L, that is called the electrical length. And the input voltage now you can find at the generator side. So this is the voltage for at any point. This is the voltage current at any point. Now if you know the gamma L, Z naught and gamma, the voltage and current at any point on the line can be determined from the above two equations. Now the input impedance or input voltage is V at Z equal to minus L. You can use the voltage division law here, and once you know the input impedance Vg is this, and that is equal to gamma L. So you can write V0 plus equal to. So you can use this formula. You don't need to use this formula for solving any circuit. So we have to find maximum and minimum voltage. So Vmax and Vmin. So you see for lossless transmission line, we got expression like this. So now if you take V0I magnitude and want to find the Vmax, so take this magnitude and this magnitude. As you see here, this magnitude will be highest if this value is 1, positive 1. So this value will be positive 1, then you will get magnitude highest. So that means V will be maximum if this amplitude of this have got the maximum value. Similarly, V will be minimum if the amplitude of this 1 minus this will be gives you the minimum. So that we have used this same method for finding the electric field value for maximum and minimum. Now for current expressions, you know that when voltage is maximum, current will be minimum, and when voltage is minimum, current will be maximum. Now let us find the standing wave ratio. We simply use lowercase s for SWR, and SWR is equal to the magnitude of voltage to the maximum magnitude of voltage to the minimum magnitude of voltage, and we also can write it like 1 plus gamma L, magnitude of gamma L, 1 minus magnitude of gamma L, or simply you can write, as you know, the magnitude of gamma L is equal to the magnitude of gamma at reflection coefficient at any point. So you can write simply this expression. For lossless transmission line, you can find the impedance at any point can be put in the form like this, Z0, and Z is Z0 on plus gamma, 1 minus gamma. So this is how we can find the impedance at any point. Where gamma reflection coefficient at the same point on the line where the impedance is to be calculated. And this is the formula for finding gamma. So you don't need to know this formula either. And we have to find the SW impedance. So at the point where V is maximum, we have the formula like Z equal to Z naught 1 plus gamma L divided 1 minus gamma L. And this is the standing wave ratio. So you can write S times Z naught. And at the point where V is minimum, we have Z equal to Z naught 1 minus gamma L 1 plus gamma L. So you can write Z equal to Z naught over the SWR. So this is the relationship between the impedance and standing wave ratio. Now this is the formula for finding power. So this is how we can find the power. Power is equal to half V or I conjugate. So as you know, we have V equal to this and I equal to this. So I conjugate will be Z naught conjugate, E gamma Z conjugate and reflection conjugate. So if you use this formula, you will come up with this very hard formula here. It is very complex formula. So we don't ask to find power anyway, but you have to know the reflection coefficient. We can measure it in terms of power. So there is the formula for reflection coefficient equal to P minus over P plus. Reflection coefficient is square. P minus is the reflected power and P plus is the incident power. And now we can think about some special cases for lossless transmission line. For example, if you take a short-circuited transmission line, then what will happen? So we'll think about the input impedance. Also, we'll think about the reflection power, and so think about the short circuit transmission line. So let's say we have a transmission line here and we shorted it. So this is a short circuit transmission line. So if it is a short circuit transmission line, then what will be the input impedance? Let's say this is the, we can find the input impedance, and input impedance, the formula is Z naught ZL plus Z naught tan beta L over Z naught plus ZL tan beta L. Now, if you think this is short circuit, that means the impedance at this point will be 0. So if this impedance is 0, Z L equal to 0, ZL equal to 0, if you put 0 here, and if you put 0 here, then this Z naught will be cancelled out. So you'll get input impedance equal to Z naught tan beta L. So we are getting input impedance equal to Z naught tan beta L. So this is very interesting here. The impedance has only imaginary part. So it could be inductive or capacitive. Inductive or capacitive. Capacitive. Why it is inductive? If tan beta L, as you know, tan beta L varies from negative infinity to positive infinity. So as tan beta varies from negative infinity to positive infinity, if it is negative values, tan beta L is negative, then you will get capacitive. If tan beta L is positive, you will get positive values. So that means you can produce a short circuit transmission line is nothing but is a inductor or a capacitor. So it can be used as a inductor or capacitor. You can produce any value for inductance and capacitance by using a short circuit transmission line. So this is very interesting that you can use a short circuit transmission line as an inductor or capacitor. So sometimes, for example, if you need 1.5 Henry inductance not available in the market, that time what you can do, you can make this type of inductance by using a transmission line, short circuit transmission line. Only you need to set the length of this transmission line properly so that you can come up with 1.5 value, value, this reactance value. So I shouldn't say millihenry, I should say 1.5 ohms or something like this. Similar, then for that case, the reflection coefficient will be ZL minus Z naught. This as ZL equal to 0, so it will be negative 1. So 100% power will be reflected back. So if the signal is going there and it is short circuit, then same signal will be reflected back. So, and standing wave ratio will be infinity. As you know, standing wave ratio S is equal to 1 plus gamma L divided by 1 minus gamma L. So as gamma L equal to negative 1, so this will be 0. So this will be 1 plus 1, 2, 1 minus 1 is 0, so 2 over 0 infinity. And now the power is 0 because power loss will be 0 because it is short circuit. So there is ZL equal to 0, so power loss will be 0. So that means the reflected power and incident power will be this. Now ZSC, the short circuit impedance will be infinity. So you can find an infinite value for ZSC, the value. If you put L equal to lambda over 4, if you put L equal to lambda over 4, so as you see, tan beta L is equal to tan beta equal to 2 pi over lambda and L equal to lambda over, so I'm putting lambda over 4, so that will be pi cancels, so lambda cancels and 2 and 4 cancels, so 10 pi over 2. 10 pi over 2 is equal to infinity, so right. So if you put lambda over 4, you will get infinity impedance, and if you put lambda over 2, your impedance will be 0. So just it is uh, switching between 0 to negative in positive infinity. So if you want to make 0 impedance, short circuit impedance equal to 0, then you have to put the length equal to lambda over. For example, if you want to make 0 impedance here, so this length should be lambda over 2. If you want to make an infinite impedance open circuit like this or infinite impedance, then this length will be lambda over 4. Now open circuit transmission line. So if you have an open circuit transmission line, like a transmission line that is open, here you have open. Then open circuit transmission line, the input impedance in a similar way you will get ZO cotangent beta L. So cotangent and tangent just are reciprocal, right? So that means it also can have can provide you any value for capacitance and inductance. So if it is negative infinity, then it will be inductive because there is negative sign here. So inductive reactance. If it is positive, then you will get capacitive. So it can make capacitive and inductive. So open circuit transmission line can be used as a capacitive or inductive transmission line. This reflection coefficient will be this, standing wave ratio will be infinity, loss is 0, and you will get the open circuit transmission impedance is 0 if lambda L equal to lambda over 4, and is if it is L equal to lambda over 2, it will be 0. Now ZOC and ZSC. So ZOSC was tan beta L and ZOC is cotangent beta L. So you can write multiply this, you will get ZOA square. Now matched load. If ZL and Z no are same, so ZL if ZM is same, for that case you will get reflection will be 0 because ZL minus Z naught, ZL plus Z naught. So it is ZL and Z naught same, then reflection will be 0 and there will be no standing wave because reflection is 0, and so it is meaning that the total power will be transmitted, so no power will be reflected back. Duet can find the maximum power transfer by using this formula. Now, a half wavelength line. If you use half wavelength line, so if you have a half wavelength line, the line equal to lambda over 2, lambda over 2. So what will happen? So lambda over 2, the electrical length will be beta L, beta equal to 2 pi over lambda, lambda over 2 equal to pi. So now, if you have a half wavelength line, that the input impedance will be Z naught ZL tan beta L, beta equal to pi. So this will be 10 pi, and this is 10 pi. So 10 pi is 0. So you'll get Z naught cancel out equal to ZL. So that means if you have a half wavelength line, so if your wavelength is on half, lambda over 2, this length wavelength is lambda over 2, then the impedance at this point is equal to the load impedance is equal to the load impedance. So ZL is equal to Zin. So if you measure at lambda over 2 distance, you will get ZL equal to this. So if you has a ZL here, then if you come to this point, then ZL will be get changed, increase or decrease, and again it goes to ZL, and again it goes change, and again after lambda over 2, again it goes to ZL. So let's say ZL, then it will ZL, then it will go like this, then it becomes ZL again. So let's say this is your Z cell, it will be ZL. So ZL, it goes like this. So if you plot these things, you can see if you plot this one, you will get that you will come up with these things that ZL is changing. Now quarter wavelength line, if you tell L equal to lambda over 4, then it will be pi over 2, and 10 beta L will be pi, infinity, pi over 2 is infinity. So that for that case, Z in will be Z over square ZL. So at that case, if you check a quarter wavelength transmission line, then the uh, input impedance will be ZO squared over ZL. So if ZL equal to 0, then input impedance will be infinity for open circuit. If ZL equal to infinity, then input impedance will be 0, like short circuit. So electrical length beta L equal to pi over 2, 90 degrees. Now this is an example here. You can try to solve these examples. The formulas are given. So you can practice how to solve these examples here. So the solutions is given here. You need a calculator to solve this.